What's up, y'all? So today we're going to be talking about the pigeonhole principle. So the pigeonhole principle is basically a way for us to bound the number of items that we put in certain boxes. We'll go over what that means in more detail later, but first, forget the math, look at these wonderful pictures. So these are pictures of a marble sorter, which is basically a machine that, as an input, takes a bunch of marbles of different colors, 7 different colors. At its top, you let them fall through some sort of like grid maze-like pattern here, and they fall neatly sorted into 7 different boxes. So there are a few interesting things to note here. One, it's fake. This is CGI. You can't actually do this. I feel like it should be pretty intuitive, like given that these marbles are randomly distributed, and also these images, like don't look entirely real. Um, but yeah, this like is not a thing. So let's get that out of the way first of all. But second of all, more coolly, we can tell that some of these boxes have lesser marbles than others, but there's a baseline. And in fact, intuitively, there should be a baseline for the number of marbles that one of the boxes must have. In other words, if we start out with 14 marbles, we're going to know at least one of the boxes must have at least 2 marbles. Because if all the boxes have like only 0 or 1 marbles, then there aren't enough marbles in total. So this is the pigeonhole principle. Basically, if we take a bunch of items called pigeons for some reason, and we try to stuff them into a lesser number of cubby holes, pigeonholes, uh, we're going to have to end up putting at least 2 pigeons or multiple pigeons into a singular hole. So it's a reasonably intuitive concept, um, but let's try, and see if we can formalize that. So let's say we start with 9. Wow. So 9 pigeons, and each one of them has a little beak, and we want to put them into 3 cubbyholes. So cubbyhole 1, cubbyhole 2, and cubbyhole 3. And we're gonna ask ourselves, if we look at the cubbyhole with the most number of pigeons, what is the least number of pigeons that it could possibly have? In other words, we want to minimize the number of pigeons in the most populous cubbyhole. So if that was a bit confusing, don't worry, but let's go through a method. Basically, we want to make each cubbyhole not be as crowded as possible. So we'd start by putting, 1 pigeon in the first cubbyhole, and because we don't want the cubbyholes to be too crowded, we just put the next pigeon and the next one and the next pigeon and the next one. But now we have to go back, right? Because we can't put pigeons in new cubbyholes; they're gone. Oh yeah, and we're just gonna say that these 3 pigeons are all in the cubbyholes. Um, we don't have any more space. So even if we want to minimize crowding, we're going to have to double up pigeons. And similarly, we're going to have to triple up pigeons. And remember, the reason that we kept putting pigeons in different cubbyholes is because we want each cubbyhole to be like to have as little crowding as possible. So of course we're going to try to spread out the pigeons more evenly. But we can see here that even though we try to have as little crowding as possible, each cubbyhole still has 9 over 3 or 3 pigeons. And in fact, intuitively we can show this and we can also prove this, that no matter how we distribute the pigeons, at least one of the cubbyholes is going to have at least 3 pigeons. So let's see if that makes sense. Suppose all of the cubbyholes had less than 3 pigeons. Suppose all of the cubbyholes had x is less than 3 pigeons. Then there'd be 3x pigeons in total, and this would be less than 9 since x is less than 3. But we know there are exactly 9 pigeons, so this can't happen. And this is a special case of the pigeonhole principle, which basically just goes to, so if I can erase this for a second. If we've got n items, and x spots to put them in, at least one spot has the ceiling of n over x pigeons. So suppose in this case, instead of, so note that down for a second, remember it. Suppose that I add another pigeon to this game. Yeah, suppose I add like a special highlighter pigeon. Now, I still want to make the cubbyholes as little crowded as possible. So I'm gonna have to add him to one of these cubbyholes. Wherever I add him, that cubbyhole is gonna have 4 pigeons. And that's an example of the pigeonhole principle. In this case, n, our number of items, is 10, and x, our number of cubbyholes, is 3. So at least one cubbyhole is going to have the ceiling of 10 over 3 or 4 pigeons. Alright, I hope that made some amount of sense. So let's move on to an example problem. So we have 52 people in a room. What's the largest value of n such that the statement at least n people have birthdays in the same month is always true? So this is another place where we could apply the pigeonhole principle. So suppose that we've got our 52 people all lined up, 52 people, and we've got our 12 months. And these are going to be our cubby holes. And basically, we want to toss those 52 people in the 12 months, and we want to do so in a way that minimizes crowding, right? Because if we want to say at least n people have birthdays in the same month, regardless of the distribution, then that's going to have to hold true in the case where there's the least amount of crowding, where the least number of people have birthdays within the same month. So how are we going to achieve least crowding? Well, it's pretty simple. You put person 1 in the first one, person 2 in the second, and so on and so forth. And we just keep doing this until we have to cycle back. And then we cycle back. And we keep doing this. We keep doing this until we've put four people in each box. In other words, until 4 people are in each month. And again, the reason we're doing this is to minimize overlap. Since we want to make a statement about a lower bound on the overlap, we want to figure out what the minimum possible overlap could be. So we've just established that when we're trying to minimize crowding, when we're trying to minimize overlap, at least one box is going to have at least 4 people. But this 4 was just 48. Right now we've got 48 people on there. We still have 4 more to go. Now we could put those on 1, 2, 3, 4, 5, and that's how we do it in a way, again, that minimizes crowding. So here we can see that even if we distribute the people in a way that minimizes crowding, at least one box is going to have 5 people. At least one box or 1 month has 5 birthdays. Wow, that's horrible exclamation mark. There we go. And this is an example of a pigeonhole principle where n, our number of items or number of people, equals 52, and k, our number of boxes or number of pigeonholes, or in this case number of months, equals 12, and the least number possible is 52 over 12, ceiling of that, which equals 5, since we know that 48 over 12 equals 4. And thus, our answer to this question is going to be 5. Alright, thank you so much for watching, y'all. I hope you guys learned something about bounding and the pigeonhole principle, and if you ever try to make a marble sorter at home, it's going to be a lot easier if you use CGI. Alright, have a good day.